In this video, we will explore the concept of relativistic energy. As we stated before, special relativity has two fundamental postulates. 1. The laws of physics are the same in all inertial frames of reference. 2. Light travels in a vacuum with the same speed c in any direction in all inertial frames. In order to be a complete theory, special relativity must return to the classical cases, without breaking its fundamental postulates, when the involved speeds are much smaller than the speed of light. In this sense, energy is one of the most important concepts in physics, as it determines fundamental interaction in nature. Then, let's focus on the definition of energy. If you push a box with a specific force F over a determined distance d, then you can define the work, W, as follows. But, from the work should be equal to the final kinetic energy of the system. And assuming a one-dimensional displacement in U, we have. Also, we know that the force is defined as the derivative of the momentum with respect to time. But, in the previous video, we saw that the relativistic momentum differs from the classical by the relativistic factor. Then, if we insert this into the last equation, we have the following. Finally, the relativistic kinetic energy has the following form. Note how the relativistic kinetic energy keeps its classical characteristic. This is, the product of the mass times the square of the speed. Furthermore, note how the speed of the moving object is now in the relativistic factor. Now let's turn our attention to the right side of the definition of the kinetic energy. We can see that if we rearrange the equation, we get the following. But, this equation has the form of the total energy. Then, we define the total relativistic energy in the following way. And the relativistic kinetic energy as follows. Again, don't forget that in both cases, the relativistic factor is using the speed of the body. Then, a very interesting case is when the speed of the body approaches to zero. In such a case, if U tends to zero, then the relativistic factor becomes 1, meaning that the total energy is simply. This equation means that energy is the same as mass, only scaled by a factor of c square. More important is that this equation says that the amount of energy contained in the mass of a body can be released, and should be a giant source of energy, either for human consumption or destruction. By the way, this equation is probably the most known equation in physics. On the other hand, if the speed of the body approaches to the speed of light, then the relativistic factor becomes infinite, meaning that the energy is also infinite. In this case, we reach the following conclusion. A body with mass needs an infinite amount of energy to reach the speed of light. Then, under our current knowledge, we reach the same conclusion as in previous videos, it is, the speed of light is the limit for interactions to propagate. Now, let's analyze the kinetic energy. As discussed in previous videos, we need to get the classical results when the speed of the body is much smaller than the speed of light. Then, if U is much smaller than c, and using the binomial expansion of the relativistic factor, we get that the relativistic kinetic energy is the same as the classical case. confirming one more time that special relativity is a complete theory. Now let's solve an example to see how the total relativistic energy works. Example 7. Calculate the rest energy contained in 1 gram of mass. Could you solve it? Answer. We know that the total relativistic energy for a body at rest is the following. Using the mass in units of kilograms and the speed of light in meters per second, we get. Then, the total relativistic energy at rest is. In order to have an insight of how large is this amount of energy, we can say that it is of the same order as the energy released in the atomic bomb dropped on Hiroshima in 1945. A natural question should be, if the atomic bomb dropped on Hiroshima had about 64 kilograms of nuclear fuel, why the release energy is of the same order as that released by 1 gram of matter? The answer is not trivial at all. As there are many factors to consider, we can say, for simplicity, that the efficiency of such an atomic bomb was less than 1.5%. This means that only a small fraction of the nuclear fuel actually generated the nuclear reaction. We all know the horrible results. Finally, we explore the relationship between the relativistic energy and momentum. We know that the total relativistic energy is defined as follows. In some textbooks it is possible to find the term relativistic mass that represents the product of the resting mass times the relativistic factor. Also, the resting mass is usually designated as m sub 0. It can be proven that the relativistic energy can expressed in terms of the momentum as follows. This equation opens a new venue of possible phenomena. Note how it allows a body without mass to have energy. Furthermore, such an energy is proportional to its momentum, as we expected from classical physics. This was a huge finding, because it implies that light can be conceived as a massless particle that will be a vital part of quantum mechanics. In the next video, we will explore only an overview of general relativity, as it is a very complicated theory that is out of the scope of this course. Stay tuned.